Let's start with simulation again in the second lecture. Now, in the last lecture, I had mentioned that I thought this is going to be a likely to be a one lecture topic, but clearly, I think I spent quite a bit of time explaining Monte Carlo simulation, and that's fine. I think that is a topic that is good for you to know. So we'll finish off. We'll actually go through the discrete event simulation in detail, um, and um, and we'll finish off simulation today. Okay. All right. So this is the second lecture of simulation. And what we are going to look at in detail today is discrete event simulation. Okay. Now, to illustrate the different what discrete event simulation is and to illustrate the different steps in building a discrete event simulation, I'm not going to just sort of talk about it or sort of write here. I will actually show you a simulation that I have developed of a simple simulation that I've developed of the operations of a doctor in a clinic who serves two types of patients. Okay, and I will use that to show you the different aspects associated with developing a simulation. Okay, so this is, if you remember, one of the four types of stochastic simulation. and and this is and the reason why we are devoting an entire lecture to discrete event simulation is because, as I mentioned, it is the most common and widely used type of simulation that is used to analyze manufacturing systems. Okay, all right. We saw what Monte Carlo simulation is. Monte Carlo simulation is you develop a mathematical model of the system, and when the model becomes to and then when some of your parameters are random variables, and if if the function is so complex or the distributions are so complex that you cannot analytically derive what the distribution of the output of that function is. So if you have a function y equals f of x, then what you want to estimate via Monte Carlo simulation is y, and you do it when either f or the distributions of the components of x are complex enough that you cannot derive the distribution of y analytically. In that situation, you use Monte Carlo simulation uh, to estimate the distribution of y. Okay, all right. So discrete events, and we also saw agent-based simulation, where in agent-based simulation, the main idea, as I said in the last class, is to examine the effect of individual level interactions in a population, right? So you have a bunch of individuals who belong to some population. So for example, it could be if you're talking about COVID-19, that's pretty much everybody, for example, in a city or in a district or even in a small locality. You want to examine the effect of individual level interactions within that population on population level outcomes. So for example, so let's say that you have a population of 200,000 people who live in a certain locality in some city, and there is some set of people, for example, that exhibit a certain behavior, right? So you want to see what is the impact of that behavior on the set of 200,000 people who live in that locality, right? So that is agent-based simulation is used to simulate individual the effect of individual interactions on the population as a whole. All right, and I use the example of our research on hepatitis C to illustrate what agent-based simulation is. All right, I'll get back to a slightly more I'll actually discuss that a little bit more in detail once we actually finish with discrete event simulation, time permitting. Okay, so let's start with discrete event simulation. So what do you do with discrete event simulation? What is discrete event simulation? So, as the name indicates, in discrete event simulation, keep in mind what we are talking, it is called discrete event simulation and not discrete time simulation. So, you don't necessarily deal with discrete times, but instead you deal with discrete events. Okay, so now what does that mean? So what you do is you move from event to event. So you simulate the occurrence of events, and the simulation is advanced. So you move forward in the simulation in time by actually moving from event to event instead of moving from, for example, time step to time step. Okay, although that can also be done, but in discrete event simulation, typically what you do is you move from event to event. And I'll show you an example. Okay, so so let me give you an example. So let's say that you have a single, let's say you have an MM1 cube, right? Simple. So you have an MM1 cube and you want to simulate the operation of this MM1 queue. So what does that mean? You have one server, right? So this is the server and jobs arrive to this server, right? So they come in here, they get processed and then they depart. All right, so it's MM1. So jobs are the distribution of interarrival time. So the jobs is exponential. The distribution of the process rate is Poisson, which means the process time is exponential, right, of the server. So if you want to simulate the operation of this system, and if you want to, the best thing to do is to actually conduct a discrete event simulation. Okay, and I'll tell you why. Okay, so what you do in a discrete event simulation is, let's say you start the simulation at t is equal to 0. Okay, now at t equals 0, what you do is you then schedule the next arrival of the arrival of the first customer or the first job. Okay, so let's say that, so what you do for that is you have an exponential distribution, okay, of interarrival time. So I'm going to call this ta, so which is exponential of some lambda a. Okay, from this distribution you get a single value of the interarrival time. Let's call that ta1. Okay, and what you do is you sample from this, and this ta1 becomes the arrival of the first customer. Okay, so then, so this event, the arrival of the first customer, occurs at ta1. Okay, so let's actually, let me just write this down a bit more clearly. ta1. Now there is no other customer, this is the first customer, so the uh, so the service of the customer begins immediately. Now, so you move to, what you do then is you don't look at any time instant between t equals 0 and t is equal to ta1. So you move directly from here to this time point. Okay. Now, when you schedule the arrival of the first customer, okay, you also have to schedule their service time. For that, you sample from the corresponding exponential distribution. Let's call that ts. And from this, you draw one sample and you simulate, and you get the service time for this particular customer. So the end of the service, now once you have one customer has arrived, you, what you want to know is, you know when the service is going to end, which is ts1, right? And then what you want, but you also want to know when the next customer will arrive, right? So because the next customer can arrive either before the service of this customer, of the first customer, is complete, or after the service of the first customer is complete, right? So it can be any time. So in order to know which event to move to next, you have to figure out when the next customer is going to arrive also. So for that, what you do is you actually take another sample from the distribution of the interarrival time of the customers. Okay, so you generate a ta2. Okay, now, and you, similarly what you do is you also sample a service time for this customer, so you get a ts2 also. Okay, now it could be that the third customer can arrive even before the first customer completes their service, right? So typically what is done is you simulate the arrival of a large, you actually schedule the arrival of a large number of customers. Okay, so let's say for example 1,000 customers, so that you don't run out of customers and you can schedule their arrival. Okay, so you get ta3 and so on. Let me just write these a little more so the notation is a bit clearer. It's consistent actually. This is ta2 and that's ta3 and so on. And for each of them you also generate the corresponding arrival. You generate the corresponding service times. So now what you have is a list of events. Okay, so you have a list of events which is arrivals of various customers. Okay, and then you have the arrivals of and the service times for each of these customers. Okay, now the point in time at which the second customer will arrive, that is not T8. Remember, these are the inter-arrival times. So the point in time in simulation time when this customer will arrive is actually going to be TA1 plus TA2. Okay. Similarly, the point in time when the third customer arrives is not going to be TA3, it's going to be TA1 plus TA2 plus 3A3, because what we are sampling are the inter-arrival times and not the uh, and not the um, uh, and not the actual arrival times. Okay, so once you have the inter-arrival time, of course, it is easy to calculate. So using this, you actually calculate the point in time. Using these inter-arrival times, you actually create a list of two lists of events. Okay, so we'll call that arrival times. So what we sampled, keep in mind, are the inter-arrival times and not the service times. Service times, of course, are just the service times, so there is no need to add them. So let's say that the arrival time of the first customer is, let's call this customer number. Okay, so what you do is, this is customer number one. The arrival time is TA1, service time is TS1. Customer number two, the arrival time is TA2, service time is TS2. Sorry, the arrival time is TA1 plus TA2. This is the TA1 plus TA2 plus TA3. This is TS3 and so on. So you create a list of, first of all, the list of arrival times you create, and of course you have the service times as well. Okay. Now what you do is, the arrival time of the once you have the arrival time of this customer, plus you have the service time um, of this customer, you know when the start time of the um, when the start time of the next customer is. Okay, so unfortunately I don't have the space here to um to write down the service start and the service completion time actually here. So what I'm going to do is, I'm just going to write this down again. Hold on, just to ensure that it's clear. It's important that you understand. Customer number, arrival time. Okay, so we have service time, service start, and service finish. Okay, now customer number one, arrival time is TA1. For customer number, service time is TS1. Service start is at TA1 itself. Nobody is waiting. Service finish is going to be TA1 plus, this is the service end time, right? Plus TS1. Okay. Next, what you do is you have to figure out whether your TA1 plus TA2 is actually less than TA1 plus TS1. Okay, so if it is, then the next arrival, then the arrival time is just for this customer is just going to be TA1 plus TA2. There's no problem there. The service time is of course just TS2, so there's no issues there. But service, for figuring out service start, it actually becomes a bit more complicated. So first, what you have to do is you have to figure out whether TA1 plus TS1 is less than TA1, less than or equal to TA1 plus TA2, right? In which is going to be less than TA1 plus TS1 is actually less than TA1 plus TA2. If yes, then the service start for the second customer is just going to be TA. is actually just going to be actually a TA1 plus TA2. If not, it's it means that the customer arrives before the service actually finishes for the first customer. So the service start time is going to be TA1 plus TS1, right? So I'm just going to write that down. Okay. Now for service start, I'm just going to write down the condition. Let's You have to perform this check actually. All right. So T if TA1 plus TS1 is lesser than TA1 plus TA2. What does this mean? The server is free at the time that the second customer arrives. Okay. If the server is free at the time that the second customer arrives, then the service start time for the second customer is just serve start is just TA1 plus TA1 plus TA2, which means now otherwise, so I'm just going to write this down. Otherwise, service start for the second customer is going to be TA1, sorry, slightly confusing notation, I know, TA1 plus TS1. Okay. So if the customer arrives, so you have to check whether if the arrival time of the second customer is greater than or equal to the service finish time of the first customer, then it means that the server is free uh, at the time that the second customer arrives, in which case the service start time is as soon as that second customer arrives. If not, the service will start after the service of the first customer finishes. So in this way, what you do is you develop an event list. Okay. So let's assume for now that actually the service that this is true for second customer. So we assume that this case holds. Okay, so this case holds for second customer. Once you know this, then you can actually create an event list. Okay, so you create an event list in ascending order of the event time. So event list 1 is the arrival of the first customer. So arrival of first customer, TA1. Okay. Event 2 is, we said that it's the second case holds, right? So what does this mean? It means that when the second customer arrives, right, the uh, the second customer arrives, the server is not free, which means that the server is not free and that the service for the second customer begins after the service for the first customer is finished. What does this mean? What does this mean for the next event that we need to go to in the simulation? It means that the next event that we should go to is that the second customer arrives, right? Because what we are saying essentially is that if this case holds, it means that the second customer arrives before the first customer finishes their service. So the next event we want to go to is arrival of second customer, which is TA1 at time point TA1 plus TA2. The next event that occurs is the finish of service. So we're not considering the third event yet, of service of first customer, which is basically TA1 plus TS1. Sorry. Okay, and next is service start of the second customer, which is TA1 plus TS1. So this is a so now what you do now, of course, so these two happen effectively at the same time in the simulation. So that is not so we assume that there is no real time lag actually between the finish of the service of the first customer and the service of start of the second customer. It's a very reasonable assumption to make. So for example, if there is a line, unless there is an if the unless the second the server actually takes a break between finishing the service of the first customer and starting the service of the second customer, then we can assume for the most part that we can assume for the most part actually that the service of the second customer starts pretty much at the same time that the service of the first customer finishes, right? Now it could be that there is a scheduled break every 10 customers or something in, for example, a bank, or it could be that we can calculate the average number of breaks that a server takes after in a given time period, and we can actually model the arrival of the break itself as a separate sort of job in some sense, right? So very similar to a setup, very similar to how setups are modeled in the uh, how we actually considered the arrival of setups when we looked at the calculation of effective process time, right, for a workstation or for a machine. So we can actually consider, we can model that also, the arrival, we can model the situation of the server taking breaks after some end customers or after every 1 hour or something of that sort, by scheduling it as an event and going to that event, finishing the break, coming back, and then resuming service, right? So that can also be done. In fact, we do that actually in some of our simulations. So then what you do in the simulation is you go from, now that you've created this, or you've created this ordered list of events, you can now start at time t equals 0. Then you move to t is equal to ta1. Then you move to t is equal to ta1 plus ta2. Okay. Then you move to t is equal to ta1 plus ts1, and so on. T is equal to ta1 plus ts1 again. So that you just start there. And if you assume, for example, that the second customer finishes their service uh, after the third customer arrives, which means that the next event you will go to is the arrival of the third customer. Okay, so it's just going to be TA1 plus TA2 plus TA3. Then you move to uh, TS1 plus TS TS2, right? So and then and so on. Okay, so this is what happens in discrete event simulation. The idea is to actually schedule, is to actually create, is to schedule a bunch of arrivals of jobs. Typically you schedule the service time, you schedule the service times, you generate service times for each job, and then using this you actually create an ordered list of events, and then you move from event to event in the simulation. So the simulation clock, for example, will actually jump from t equals 0 to t equals ta1 to t equals ta1 plus ta2, t equals ta1 plus ts1, and so on. So you want actually, what you will not do is you will not actually go from you will not start at t equals 0 and then move forward 1 hour in time and then figure out what has happened in that 1 hour. Then you move to then you actually move to the second hour and then you figure out what has happened and so on, right? And why should you? When you know when the events are happening, the events are of the ones that are or of the events are what are of interest, right? So why would you actually go from time step to time step unless you're scheduling your events to happen also to occur at every time steps? And we do that actually, and I'll talk about that later. But and you can do that. You can sort of simulate events to occur at specific time steps, at regular time steps, instead of actually sampling them from a distribution. But that is less likely. So most often what you do is, as I said, you simulate the arrival of jobs, you generate service times using the scheduled arrival times, as well as the process times. You create an ordered list of events, and then you move from event time to event time, and that's why it is called as discrete event simulation, because you're going through, what you're actually doing is you're actually going through a ordered set of events, which is a discrete set, right? It's a discrete set of events. And typically what you do, the question is, okay, how do you stop the simulation? So you can, for example, either if you're simulating for example, an MM1 queue, you can say that the queue actually runs for 8 hours, right? So you can simulate the a case of a vendor, for example, right, who has maybe like a chai vendor who operates from 8 a.m. in the morning to 5 p.m. in the evening with a 1 hour break, for example. Okay, so that is one example of a, and you can just stop at t is equal to 8 hours. Okay, and you can keep running the simulation until you run out of time. Okay, so now I hope that you have a sense of what discrete event simulation is. I'm actually now going to show you a discrete event simulation that I've developed that illustrates these ideas, and then we will and then I'll sort of discuss what are the important steps involved in developing a discrete event simulation. Okay? All right. Now let me show you. Okay. So this is a simulation that I have developed of a doctor operating in some clinic where two types of patients come. Okay, you have a single doctor, and then you have two types of patients. Now I have used the software SymPy. Okay, so I've coded this in Python. There's a package called SymPy that actually does all of this ordering of events and so on, as long as you sort of create the process of arrivals and the process of providing services, it actually just creates the order list of events and does the job of stepping through the ordered list of events, and then it generates the outputs as well. So you don't actually need to do that process yourself, but I will actually show you how the ordered list of events is created. Okay, by running this. So what I'm going to do now is I'm going to very quickly just run the simulation and show you those ordered list of events. Okay. So let me just very quickly take you. So you have, this is the simulation environment that is running, that maybe simulate, that is sort of the clinic environment. It has a single resource, which is the doctor, which I have called doc here, a single resource, which is why capacity is equal to 1. I have two types of patients. Let's call them outpatients and inpatients, or we can just call them patient type O and patient type I. Okay. Now I'm defining a arrival and service process for each patient. Okay. So I'm saying that, for example, okay, that's what is happening here, and I'm not going to go into the details of this. But what I'm doing is I'm recording here the arrival time of the patient. I'm recording and that's what I'm recording the service time of the patient. I'm recording the arrival time of the patient. I'm also recording the service, I think the start time. This is the service start time, if I'm right, actually. Yeah, that's right. So this is the service start time, PT1 ST, and the uh, wait time of the patient. Okay, so these are the things that I'm recording. Now I'm just going to, and similarly for patient 2, I'm doing the same thing for patient, so for patient type I, and then I'm creating an arrival process. So I'm generating 10,000 patients of type O, and I'm generating 10,000 patients of type I. Okay. Uh, Here I'm just calling them 1 and 2. And then, but to keep things simple, I'm only running the simulation. So environment.run does that. I'm only running the simulation for 100 time minutes just to show you a list of events that we can sort of step through quickly. Okay. And then what I'm doing is I'm just showing the list of, I'm calculating some outputs, which is technically the utilization. I'll come to that later, and I'll come to this part also later. And then I'm actually just printing out the list of events. So let me just run this. Okay. So as you can see, this is sort of the event list that is created. So the first patient arrives at 5.19. Let's call it minutes. Okay, it's at 5.19 minutes. Their service, this is the first patient, so service starts immediately. Wait time is 0, and the first patient who arrives is actually a patient type I. Okay, the service duration for this patient is 1.63. All right. Now, what does this mean? And the second patient arrives at 8.88. All right. So, what does this mean? This means that this patient actually um, This means, now, so second patient arrives at 8.88, but the service duration of the first patient actually finishes at 1.63 itself, in 1.63 minutes itself. So the service actually finishes at 5.19 plus 1.63. Okay, so that is the service end time, which I have not noted here. So the service start of the second patient can start when they arrive itself at 8.88. All right. Now let's look at the next patient. The next patient is going to arrive at 9.22. Now the service duration for the second patient is 8.88, is actually 2.39. The arrival time is 8.88. So the service finish time for the second patient is 8.88 plus 2.39. Okay. So the second patient will finish only at 11.276. Okay. So the service start of this third patient. So the third patient will start the service only when the second patient finishes at 11.276, even though they have arrived at 9.222. So they have a wait time of 2.054. So as you can see, we actually step through the list of events in this way. What happens to the fourth patient? The fourth patient arrives at time 17.838. Okay, that is of patient type O. The fourth patient arrives at 17.838. Their service duration is only 1.049 minutes. Okay. Now, what is the service duration of the third type of patient? The third type of patient, the service duration is only 11.998. So their service will finish very quickly, right? So by I think around 12.27 itself, roughly they will finish off. So this fourth patient will not have any wait time, which means the service can start immediately at 17.83, right? Okay. Now, what about so similarly, for the rest of the patients, actually, what you will find is that uh, uh, you're going to have a bunch of actually O patients, and in all of their cases, the service durations are actually much smaller than their inter-arrival times, right? So, for example, service duration is 0.904, arrival time is 21.982 minus 17.838. Okay, so here this arrival time actually corresponds to this your TA1 plus TA2, TA1 plus TS3, and so on. All right. Now, so that's what happens here. So you step through this list of events, and eventually you stop at time equals 100, right? So so we actually stop at let me show you. This is 95.639 is the arrival of the last patient, and what we do is the service duration is 0.823, so the service actually gets over at something like 96.4 itself. But then the arrival of the next patient is most probably scheduled after 100 minutes, so we don't go there because we run the simulation only until 100 time units. Okay, so we pretty much stop here. Okay, so this is what a discrete event simulation looks like. Okay, now, so once again, what we do is we create an ordered list of events and then we step through those events. I'm just going to very quickly go through for the first three events once again. Okay, just to sort of avoid any confusions. First patient arrives at 5.19. The service duration is 1.63. Second patient arrives at 8.88, but service of first patient will finish at first 5.19 plus 1.63. So, which is actually less than the arrival time of the second patient. So, second patient has no wait time, which is reflected here. So, uh, now their service actually lasts for 2.39. So, their service gets over at 8.88 plus 2.39, which is 11.276. The third patient, on the other hand, arrives at 9.22 only, okay, which is less than, which actually is before the second patient finishes their service. So the third patient has to wait for some time, which is reflected here. Okay, and hence that is recorded, and so you can and you sort of similarly what you do is you just run through you create a list of events and then you step through the events. Now similarly, I can run this until 10,000. Okay, and then let's see what happens. Now I'm actually, you can see that I'm having a lot more wait times here, but in general it does seem you have a lot more zeros than you have wait time. So in general you see that it's not running at anything close to 100% utilization. Okay, so what I do now is I collect one of the things that I'm interested in is I want to understand what the utilization of the server is. But typically, and as we sort of discuss in queuing systems, when you talk about the behavior of queuing systems, you want to figure out what the steady state behavior is of queuing systems. Okay, so now I assume that after 5,000 time units, the system hits steady state. So I start collecting outputs only after 5,000 time units have passed. So what I do is I collect the service times. Okay, so the fourth is the 1, 2, 3, 4, and the so what are the things I record here? Yeah, let's see. So I record. Sorry, yeah. So I record actually the service times, right? So the service times actually I record for each patient after 5,000 minutes have passed. After the arrival time of the patient, which is 2, right? 0, 1, and service start time. So PT2 is the service PT2 underscore ST and PT1 underscore ST are the service start times. So this is when the service starts. So after the service start time is greater than 5,000 units, so any patient who has received service after 5,000 units, after 5,000 units of time have passed, I record their service times because that is the amount of time for which the server is busy. Okay, so then what I do is I sum all of that up and I divide by 5,000. So 5,000 units of time is the steady state duration for when the server is available. And what I do is I calculate the total amount of time for uh, total amount of time during those 5,000 minutes when the server is busy. Okay, that I collect and then I divide it to get the utilization. So it's a long run fraction of time over which the server is busy, right? So that is utilization, and I get the utilization as 0.43. It's around 44%. So utilization is 44%. So what do I do? So I decide that the simulation reaches steady state after 5,000 units of time, and so for all servers whose for all patients whose service starts after, and that's what I've indicated in st.j2. Okay, so this is the service start time, this is the service time itself, right? So the service start time for the patient, this is the service time itself. That is what is recorded here. So so for all patients whose service starts after 5,000 units of time, I actually record their service times, which is what is recorded here, 0, and then I sum it up for both types of patients and divide by the total amount of time for which the server is available. So this is the total amount of time for which the server is engaged, which is the service times, divided by the total amount of time for which the server is available, which is going to be your utilization. And so I report the outcome of interest, which is utilization here. I can also similarly calculate. Uh, I can also similarly calculate the um, waiting time as well. Okay, so for that, I just need to sort of average out this waiting time. That's it. So I just need to average out this average waiting time for, let's say, all patients for both across both patients. I just need to find the average waiting time. So that I can just actually calculate as, let's see, print. Um, I have NumPy here, right? Yes, I do. Yes. Okay. So np dot mean of st total, um, what is the column I want now? Let's say I just want all rows and the waiting time, which is the fourth, 1, 2, 3, 4, 4. So third column. Let's see if we get that. Okay, so integers slices, not a tuple. Hold on. Let's just write this. So I just need to get the syntax right here. Okay, so now let's try. Yeah, I'll figure out the syntax, but you get the basic idea. I need to take the fourth column and then just average it out, right? So that's the only thing to do. Uh, or I can, yeah. So, okay, so this is an example of a discrete event simulation. Now, there are many steps to developing a discrete event simulation. There are roughly around, I would say, 6 to 7 steps to developing an effective simulation. And as I said in the last class, many of the steps that I'm going to talk about as far as developing simulations go, they are actually applicable to all types of simulations. Okay, let me very briefly actually take you through some of the things that needs to be done. Okay. Uh, so the first thing that needs to be done is you need to actually go and study the system. Okay, you need to understand. I'm going to switch back to the notes now. So steps of developing valid and useful simulation. Okay, so the first thing you have to do to develop a simulation, this is actually where I would have really loved to have conducted this in a live class where I could actually ask all of you what do you think the steps are and so on. So that is something, to be quite honest, I actually miss quite a bit the interaction during the teaching. But anyhow, let's just continue. So first, let's see. The first step you want to do, you want to use in developing a simulation is study the system. Quite simple. So you have to study the system that you want to simulate. So, for example, let's take the case of the clinic itself that I showed you, right? The clinic simulation. What are the things in this? There are basically, you can say, three entities in the simulation, right? So you have the doctor, you have patient type O, and you have patient type I. So you can think of them as outpatients and inpatients, right? So that's why I denoted them by O and I. Now you have three types of patients. You have three types of entities. But if you go to an actual clinic, you will actually find that there are many other types of entities as well. So you have a doctor, you have different types of patients, you may have nurses, you may have support staff, like there might be a pharmacist, there might be a receptionist right at the counter, there might be medical lab technicians, and so on. There might be lab technicians and so on. So if you, for example, go to the IIT hospital itself, you can see that, right? So you have somebody at the reception, you have doctors, you have nurses, you have support staff, you have cleaners. There's so many different types of people. There's a pharmacist, there's a small lab, there's a phlebotomist who, which is the technical term for somebody who actually collects samples for laboratory investigations like blood samples, urine samples, and so on. So one of the things you need to do when you're developing a simulation is first you need to decide what are you going to include in your simulation. Okay. Uh, Once you decide what you're going to include in the simulation, you have to figure out, so what are the specific processes and entities to include in a simulation. In the simulation of your system. So you may not want to create a simulation of every single entity in the system, right? So instead you have to decide what are the key types of entities you want to include in your system and then just put them in. Then once you have figured this out, you have to understand the process flow. or the operational patterns of the system. Let's write that down. Process flow of your system. Now, here, when we say the reason I put the system here, uh, the reason I sort of put the system in double quotes here is that for example, let's say that we want to look at the IIT hospital, right? And instead, what we do is instead of looking at the entire hospital, we have decided that we're actually going to focus only on the doctors and the patients. So your system now reduces to only the set of doctors and your patients. Okay. So now, and this is for the system in the context of the simulation. The system itself, the IIT hospital system itself is much bigger. But the analysis of interest here right now is the it could be the doctors. On the other hand, it might be that you want to develop a general purpose simulation of the hospital, right? So that could include, again, there you have to make a decision. And in that case, so if you want to develop a general purpose simulation of the hospital, again, you have to decide, are you only going to include those who are involved in provision of medical care, or are you going to actually involve everybody? If it is only those who are involved in the provision of medical care, then you are probably only going to include doctors, patients, nurses, lab technicians, pharmacists, right? Because all of these are different components of medical care. But you may not, for example, include cleaners, right? Or maybe there's a clerk who actually manages the inventory of medicines and other medical equipment and so on. So again, you have to make that decision. So you have to decide what is the scope of your analysis, and then you have to think, and then you have to figure out what the system is, what are the entities and the processes that you're going to include in your simulated system. Okay. So when I put the system in double quotes here, I mean the simulated system. Okay. And understanding the process flow of your system, that typically involves creating, for example, maybe like a process flow chart. What does this mean? So, for example, what is the process that a patient follows when they come into the hospital? So, they may come into the hospital, they may go to the receptionist first, then they go to the waiting area, then they go to the doctor, they see the doctor. After they see the doctor, some of them may exit directly, some of them may go to the pharmacy, some of them may go to the lab, and then they may go to the pharmacy. So, you have to figure out what proportion of patients go to the pharmacy, what proportion leave directly, what proportion then go to the lab, and so on. Okay. Uh, so there are many different components in the process of developing a simulation. Okay. Now this is yeah. So you have to develop some sort of a flowchart. Uh, Now again, uh, the question is, okay, how do you decide what are the processes that you want to model, right? How do you decide which ones to include? So for that, you have to actually talk to the stakeholders, people who are running the hospital, and ask them, okay, what are the operational issues that you have? uh, so it could be patient waiting time is very large, or it could be low utilization of the doctors, or it could be anything. It could be any different number of things actually. So there, based on the issues that are sort of that they raise, you then actually have to then you have to figure out what are the different entities involved in the processes where the issues are there, and then you have to make a decision of which ones to include. So this is not a science as such, but I can provide some general guidelines such as these. But yeah, figuring out what to model is as much an art, as I said, as it is as a science. And this is not limited to simulations. This applies to any problem that you want to solve. So you have to figure out you have to define the scope of your problem, right? So that is an important part of any process. Okay. So this entire exercise can be thought of as actually defining the scope of the problem. Okay. All right. So I'm actually what I'm going to do is I'm going to I'm going to continue with the rest of this in another lecture, which will take probably around 15 to 20 minutes before moving on to, I think probably around half an hour before moving on to dynamic programming. So I'm going to stop here with this because I think the rest of the for the rest of the for going through the rest of the steps, I think it will require another 20 to 30 minutes, and this is I think already nearly 15 minutes long. Okay, all right, yeah. I'll finish off simulation in the next lecture, and then we have two lectures of dynamic programming, and that should be it for the course. All right.